Good morning, everyone. So today, this first part will focus, or the lecture will focus on the gradient methods. So first of all, let's see the outline. I will introduce gradient methods. I'll talk about their main principles. Then I will go on and talk about the steepest descent method and the Newton-Raphson method. And I will finish by two tiny examples applied to the two previous methods. So first of all, as an introduction, I would say that gradient methods form a group of iterative methods to be applied to differentiable functions. And these methods commonly share the same methodology. So let D be here a vector in Rn, and xk be a point in Rn such that the gradient of f at xk is not zero. Gradient methods will iterate following a step we call S in R, which is a real number. So to do so, we define a function g of s, which is usually f of xk plus s times the d vector, the direction vector we defined earlier. The vector d here is considered as the descent direction if g prime of 0 is less than 0. So the main principles of gradient methods is that tend to differentiate g with respect to s to find the solution of the s. So it gives g prime of 0, which is equal to dt times the gradient of f of xk. And this dot product of two vectors can also be written as the product of the two magnitudes of t and the gradient of f times the cosine of theta, where theta is the angle between the two vectors, the gradient of f at xk and d. So if you suppose that the gradient of t is equal to 1, g prime of 0 is then minimized when you follow cosine of theta equals -1, which means basically that d would be just a unit vector from the gradient with a negative sign, which gives the steepest descent direction. And the main difference between all gradient methods lies in the choices of sk and dk. So I'll talk now about what we call the steepest descent method. This is the most popular gradient method. This is mainly due to its simplicity. So we consider here that dk is minus the gradient of f at xk, and therefore g of s would be equal to f of xk minus s times the gradient of f at xk. So we will try to find sk that is positive such that g is minimized. Note that the subproblem here to solve becomes unidimensional, and it's possible to show that if f is differentiable at least one time and takes finite values when x goes to infinity, the algorithm converges to a stationary point where the gradient is equal to 0. The main weakness of this steepest descent method lies in the fact that it has a slow convergence rate, and this is mainly due to the fact that we're using orthogonal successively orthogonal directions. So let's see the algorithm, how it works. First of all, we start by the initialization. We choose a starting point x0 or x0, and we let k equal to 0 and go to the main step. Now, in the main step, we may enter a terminal condition, but mainly we'll set dk, which is equal to minus the gradient of f at the current xk. We find xk, which is positive, that solves the minimization of f of xk plus sk times dk, which is becoming now here a unidimensional problem, which we call g of sk. We update xk plus 1 as xk plus sk times the direction at k, and we'll move on to the next iteration by updating the k. The terminal condition we can set would be, for instance, to say that the magnitude of the gradient of f at the xk found should be less than some epsilon, where epsilon is very small and positive, or that the difference or the increment or the improving in the f of xk plus 1 compared to f of xk is very, very marginal. Well, we can set also a set of number or a set of terminal conditions. Now, I'll move on to the next or the second method, which is the Newton-Raphson method. And this method considers the second order approximation of the function f in the neighborhood of xk. First of all, let's talk about it. q of x here, the second order approximation, could be written as f of xk plus x minus xk transpose times the gradient of f at xk plus 1/2 of x minus xk transpose times the Asian matrix, the matrix containing all second differential partial derivatives times x minus xk. A necessary minimum condition for the function q would be to set that the gradient of q is equal to 0, which gives this solution where the gradient of f of xk plus h times at xk times x minus xk should be equal to 0. And therefore, we can find the optimal step, which is to multiply the gradient by just the inverse of h at xk. So xk plus 1 would be xk minus h of xk inverse times the gradient of f xk. This method would guarantee good convergence results only if the determinant of the Asian matrix is not 0, if f of xk plus 1 is less or equal to f of xk, and the starting point is close to stationary point. Well, this closes the first part of the presentation. I'll move on now with the presentation of the code. But first of all, let me summarize what's going to happen in the second part. The steepest descent method here applied to this example where f of xk x1 x2 is equal to x1 minus 2 squared plus x1 minus 2 x2 squared starting from 0, 3. The gradient generally for f writes as follows. It's 4x1 minus 4x2 minus 4 and minus 4x1 plus 8x2. So at the starting point x naught, it's equal, which is 0, 3, we'll have that the gradient is equal to minus 16, 24. And then if we update the value or the expression of g of s, is going to be f of x naught minus s times the gradient, which is f of 0 plus 16s, 3 minus 24s, which writes as follow as 16s minus 2 squared plus 64s minus 6 squared. So if we differentiate g of s now, and we get the first derivative here, which is 8704 s minus 832, which means that s is equal to 13 over 136. It minimizes g of s. And the next point now after updating becomes x1, which is 26 over 17, 39 over 17. Well, we will see later that the execution of the algorithm leads to the solution, which is 2, 1 after number of iteration. And we will talk about the Python implementation after a couple of minutes in the next video. Now, for the application of the Newton-Raphson method to the same example, starting from the same point, we compute the gradient here, and we found it's equal to minus 1624 at x naught. We'll compute the second partial derivatives, and here they would be 4 minus 4 minus 4 and 8. So the inversion of the Hessian matrix gives the following: H inverse, which is 0.5, 0.25, 0.25, 0.25, and we get after the first iteration right away x1, which is equal to 0.3 minus H inverse times x naught is equal to 1. So we converge it only in one step here. Okay, so in the next video I'll talk about the implementation also of the Newton-Raphson method. Thank you very much for listening, and talk to you later.